There is no specific prohibition against using conduit pull fittings on 13.8 kilovolt feeders in the National Electrical Code. However, there are a few things to consider when using conduit pull fittings on high voltage feeders. Firstly, electrical safety. The fittings must be rated for the voltage and current of the feeder and must be installed in a way that maintains the electrical integrity of the system. Secondly, mechanical strength. The fittings must be strong enough to withstand the forces exerted by the conductor being pulled through them. Thirdly, environmental conditions. The fittings must be suitable for the environmental conditions in which they will be installed, including temperature, humidity, and exposure to chemicals. In general, it is good practice to use conduit pull fittings that are designed and tested for use on high voltage feeders. This will help to ensure the safety and reliability of the installation. Article 300 of the National Electrical Code covers wiring methods. The Eaton Technical Guide to Medium Voltage Switchgear and Substations can also offer helpful information. It is always best to consult with a qualified electrical engineer for specific guidance on any project. When dealing with 13.8 kilovolt systems, electrical safety is paramount. The fittings used must have a voltage rating suitable for 13.8 kilovolts. Ensure the current rating of the fitting is adequate for the feeder's maximum current carrying capacity. Proper installation is crucial. It must prevent any compromise of the system's insulation and grounding. Verify that the pull fittings meet or exceed the short circuit current rating requirements for the system. A failure here can lead to catastrophic results during a fault. Mechanically, the pull fittings must be robust enough to handle the stress of pulling conductors. Consider the weight and size of the conductors being installed. The pulling force can be considerable, especially over long conduit runs or multiple bends. Fittings should be securely mounted to the conduit and any supporting structures. Ensure the supporting structures are also adequately rated for the anticipated loads. The environment where the fittings are installed plays a significant role. If the installation is outdoors, the fittings must be rated for exposure to sunlight, rain, and temperature variations. In corrosive environments, such as those with chemical exposure, use fittings made of corrosion-resistant materials. Consider the operating temperature range of the fittings. High-voltage equipment can generate heat, and the fittings must be able to withstand those temperatures without degradation. Grounding is a critical aspect of high-voltage systems. The pull fittings must maintain the integrity of the grounding system. Ensure proper bonding between the fittings and the conduit. Use grounding bushings or other appropriate hardware to provide a low-impedance path to ground. Inspect grounding connections regularly to ensure they remain tight and free of corrosion. Conduit selection is another important consideration. Use conduit that is rated for high voltage applications. Rigid metal conduit, intermediate metal conduit, or reinforced thermosetting resin conduit are common choices. Ensure the conduit is properly sized for the number and size of conductors being installed, adhering to National Electrical Code fill requirements. Support the conduit adequately to prevent sagging or damage. National Electrical Code Article 310 covers conductors for general wiring. Select conductors with insulation rated for the voltage and operating temperature of the system. Ensure the conductor size is adequate for the load and the ambient temperature. Consider voltage drop, especially on long runs, to ensure adequate voltage at the load. Terminations must be done correctly to prevent overheating and failures. Use connectors and lugs that are specifically designed for the type and size of conductor being used. Follow the manufacturer's instructions for preparing the conductor and installing the connector. Torque connections to the specified values to ensure a reliable connection. Protection devices are essential for high voltage systems. Overcurrent protection, such as fuses or circuit breakers, must be properly sized to protect the conductors and equipment. Ground fault protection is crucial for detecting and interrupting ground faults. Surge protection can help protect equipment from voltage transients caused by lightning or switching events. Regularly inspect and test protection devices to ensure they are functioning correctly. Coordination studies are performed to ensure that protection devices operate in the correct sequence to minimize the extent of an outage. Cable pulling techniques are critical to avoid damaging the conductors or conduit. Use cable lubricants approved for the type of conductors being installed. Avoid exceeding the maximum pulling tension specified by the conductor manufacturer. Use appropriate pulling equipment, such as cable grips and pulling eyes, to distribute the pulling force evenly. Consider using multiple pulling points for long or complex runs. After installation, perform thorough testing to verify the integrity of the system. Perform insulation resistance tests to check for insulation damage. Conduct a high potential test, also known as a HIPOT test, to verify the insulation strength. Verify the correct operation of all protection devices. Commissioning involves a systematic process of verifying that all equipment and systems are installed and functioning correctly. Develop a detailed commissioning plan that outlines the steps to be taken. Perform visual inspections, mechanical checks, and electrical tests. Document all findings and address any issues that are identified. Ongoing maintenance is essential for the long-term reliability of high-voltage systems. Develop a preventive maintenance program that includes regular inspections, testing, and cleaning. Keep accurate records of all maintenance activities. Train personnel on proper maintenance procedures. Regularly review and update the maintenance program as needed. Consider the impact of harmonics on the system. Harmonics can cause overheating of equipment, increased losses, and misoperation of protection devices. Perform a harmonic study to assess the levels of harmonics in the system. Implement mitigation techniques such as filters or reactors if necessary. Safety is always the top priority when working with high-voltage systems. Ensure that all personnel are properly trained and qualified. Use appropriate personal protective equipment, such as insulated gloves and clothing. Follow lockout/tagout procedures to de-energize equipment before working on it. Maintain a safe working distance from energized equipment. Regularly review and update safety procedures. Arc flash is a serious hazard associated with high-voltage equipment. Perform an arc flash study to determine the potential arc flash hazard levels. Implement measures to reduce the arc flash hazard, such as using arc-resistant equipment or increasing the working distance. Use appropriate personal protective equipment for the determined arc flash hazard level. Label equipment with arc flash warning labels. Consider the reliability of the system. Redundancy can improve reliability by providing backup components or systems. Implement measures to prevent single points of failure. Regularly review the system design and operation to identify potential weaknesses. Maintain an adequate spare parts inventory. Consider the life cycle cost of the equipment. Initial cost is only one factor to consider. Evaluate the cost of maintenance, energy consumption, and potential downtime. Choose equipment that offers the best overall value over its expected life. Energy efficiency is becoming increasingly important. Use energy-efficient equipment and design the system to minimize energy losses. Consider using renewable energy sources, such as solar or wind power. Implement energy management strategies to optimize energy consumption. The National Electrical Code is updated every 3 years. Stay current with the latest edition of the National Electrical Code and any applicable local codes or regulations. Attend training courses and seminars to keep your knowledge and skills up to date. Participate in industry organizations and committees to stay informed about the latest developments. Documentation is essential for high-voltage systems. Maintain accurate and up-to-date drawings, specifications, and operating manuals. Keep records of all inspections, tests, and maintenance activities. Store documentation in a safe and accessible location. Cybersecurity is becoming increasingly important for electrical systems. Implement measures to protect the system from cyber threats. Use strong passwords and authentication methods. Regularly update software and firmware. Monitor the system for suspicious activity. Train personnel on cybersecurity awareness. Consider the environmental impact of the system. Use environmentally friendly materials and equipment. Minimize waste and pollution. Comply with all applicable environmental regulations. Sustainability is a growing concern. Design the system to be sustainable over its life cycle. Consider the impact on future generations. Use resources efficiently and minimize environmental impact. Emergency preparedness is essential for high-voltage systems. Develop an emergency response plan that outlines the steps to be taken in the event of a power outage, equipment failure, or other emergency. Train personnel on the emergency response plan. Maintain emergency supplies and equipment. Regularly review and update the emergency response plan. Remote monitoring can improve the reliability and efficiency of high-voltage systems. Use sensors and communication networks to monitor the system's performance. Analyze the data to identify potential problems. Take corrective action before problems escalate. Artificial intelligence and machine learning are emerging technologies that can be used to improve the operation of high-voltage systems. Use artificial intelligence to optimize system performance and predict equipment failures. Use machine learning to identify patterns and anomalies in the data. These technologies can help to improve the reliability, efficiency, and safety of high-voltage systems. Remember that working with high-voltage systems requires specialized knowledge and skills. It is always best to consult with qualified professionals for assistance. Consider the long-term performance and reliability of the conduit pull fittings. Factors such as material degradation, corrosion, and mechanical stress can affect their lifespan. Regularly inspect the fittings for signs of wear or damage. Replace any fittings that are suspect or showing signs of deterioration. Over time, environmental factors can cause the fittings material to degrade. Ultraviolet radiation from sunlight can cause plastics to become brittle. Moisture can lead to corrosion of metal fittings. Chemical exposure can accelerate the degradation process. Look for signs of cracking, discoloration, or deformation. Corrosion can weaken the fitting and compromise its ability to provide a secure connection. Look for signs of rust or oxidation. Pay close attention to areas where dissimilar metals come into contact, as this can accelerate corrosion through galvanic action. Mechanical stress can cause fittings to become loose or damaged. Vibration, thermal expansion and contraction, and physical impacts can all contribute to mechanical stress. Check for loose connections, stripped threads, or deformed components. Ensure that the fittings are properly supported and are not subjected to excessive loads. Consider the impact of extreme temperatures on the fittings. High temperatures can cause materials to soften or expand, while low temperatures can cause them to become brittle or contract. Choose fittings that are rated for the expected temperature range. If the fittings are exposed to extreme temperatures, inspect them more frequently. Regular cleaning can help to remove dirt, debris, and contaminants that can contribute to corrosion and degradation. Use a mild detergent and water to clean the fittings. Avoid using harsh chemicals or abrasive cleaners, as these can damage the materials. After cleaning, thoroughly rinse and dry the fittings. Lubrication can help to prevent corrosion and reduce friction. Apply a thin coat of corrosion-inhibiting lubricant to the fittings. Use a lubricant that is compatible with the fitting materials. Avoid over-lubricating the fittings, as this can attract dirt and debris. Proper torquing is essential for ensuring a secure and reliable connection. Use a calibrated torque wrench to tighten the fittings to the manufacturer's specified torque. Avoid over-torquing or under-torquing the fittings, as this can damage the components. Retorque the fittings periodically to compensate for settling and vibration. Consider the impact of surge currents on the fittings. Surge currents can be caused by lightning strikes, switching events, or equipment failures. These currents can generate high temperatures and mechanical stresses that can damage the fittings. Use surge protection devices to limit the magnitude of surge currents. Inspect the fittings for signs of damage after a surge event. Consider the impact of electromagnetic interference on the fittings. Electromagnetic interference can be caused by nearby electrical equipment or radio frequency sources. This interference can disrupt the operation of the equipment or cause false readings. Use shielded fittings to reduce electromagnetic interference. Ground the fittings properly to provide a low impedance path for electromagnetic currents. Regular inspections are essential for identifying potential problems before they lead to failures. Perform visual inspections, mechanical checks, and electrical tests. Document all findings and address any issues that are identified. Develop a checklist to ensure that all critical aspects of the fittings are inspected. Maintain accurate records of all inspections and maintenance activities. Training personnel on proper inspection and maintenance procedures is essential for ensuring the long-term reliability of the fittings. Provide training on the identification of potential problems, the proper use of tools and equipment, and the importance of following safety procedures. Ensure that personnel have the necessary skills and knowledge to perform inspections and maintenance tasks effectively. Consider using condition monitoring techniques to detect potential problems early. Condition monitoring involves the use of sensors and data analysis to track the condition of the fittings over time. This can help to identify trends and anomalies that may indicate a developing problem. Use vibration analysis, infrared thermography, and ultrasonic testing to monitor the condition of the fittings. Implement a proactive maintenance program to address potential problems before they lead to failures. Proactive maintenance involves the scheduling of maintenance tasks based on the condition of the equipment rather than on a fixed time interval. This can help to reduce the risk of unexpected failures and extend the lifespan of the equipment. Use condition monitoring data to schedule maintenance tasks. Implement a predictive maintenance program to forecast future equipment failures. Predictive maintenance involves the use of data analysis and modeling to predict when equipment is likely to fail. This can help to optimize maintenance schedules and minimize downtime. Use machine learning algorithms to analyze condition monitoring data and predict future equipment failures. Consider the use of smart fittings to improve the reliability and efficiency of high-voltage systems. Smart fittings are equipped with sensors and communication capabilities that allow them to monitor their own condition and transmit data to a central monitoring system. This can help to improve the accuracy of condition monitoring and enable remote maintenance. Use smart fittings to monitor temperature, vibration, and other critical parameters. Implement a data analytics platform to process and analyze the data from smart fittings. Ensure you follow the National Electrical Code.